Good morning, Year 12 single mathematicians. Just going to continue with the revision for your internal exams with a topic requested to do with exponentials and logarithms, which is chapter 14 from the pure textbook. So just going to kick off with things you need to know from this particular chapter. First thing is the sketch of an exponential curve and the sketch of a logarithmic curve as well. So the exponential one is the easier one to get your head around. So if I had to sketch something like y is equal to 2 to the x, 3 to the x, etc., then I would draw something like this. Obviously exponential curves now are more popular in mainstream media, so you might recognize this shape, but if I call this a to the x, then the only thing I need to label in is the y-intercept, which would be, if you put 0 into this, a to the power of 0 would be 1. So it passes through 1, and it never touches the x-axis. It gets infinitesimally close, but it never touches the x-axis, and we call that an asymptote. Now, the opposite of that would be y is equal to log base a of x, and exponentials and logarithms are inverse functions of one another, and the property about inverse functions when you sketch them on the same axes is that they are reflections in the line y is equal to x, and y is equal to x is the perfect diagonal like that. So log base a of x would be that reflected, which would look something like this, and that is y is equal to log base a of x. Now there's some very specific cases you need to know. The most famous exponential curve is e to the x. E is a irrational number discovered hundreds of years ago, and it's a little bit like pi, just one of those numbers that's programmed into the calculator. So you need to know that y is equal to e to the x would have this shape as well. E is somewhere between 2 and 3, it's like 2.7 something, and the equivalent or the inverse of that would be y is equal to log base e of x, which is shortened to ln x. So some special cases: y is equal to e to the x and its inverse y is equal to ln x, which is short for y is equal to log base e of x. Okay, now other things you need to know about e to the x and some of its important properties is when you differentiate e to the x, it goes to itself. So dy by dx is equal to e to the x. That's one of the reasons why e to the x is the popular version of the exponential curves, is because it, when you differentiate it, it goes to itself. However, you also need to know, if you had y is equal to a multiple, something like that, a e to the power of kx, then when you differentiate that, that almost goes to itself, but it goes to a times k e to the kx. You multiply by the multiple in front of the x. And again, that's one of the important properties about e to the x and why it is the chosen exponential curve. Moving on to logarithms though, there's a few laws you need to know. First law is log base a of x plus log base a of y is equivalent to log base a of xy. Probably should write an identity sign for that. Second one, log base a of x subtract log base a of y is equivalent to log base a of x over y. And the third and final one is log base a of x to the power of y, where the power is inside the bracket, by the way. That's equivalent to y log base a of x. And those three rules are used to solve equations with logarithms. And the last thing you need to know is the connection between logs and exponentials is the following. So if I write any index form question, something like a to the x equals y, that is equivalent to log base a of y is equal to x. Remember, in index form, that's base. That's the power of the index. The answer to this is the power. And I guess this is just called a number. The number goes in there. And that would be, you need to know this equivalence. It's probably one of the more important things out of all the rules I've just stated. There. Okay. Right, so if we can use those now to answer some questions from this chapter. So e.g. number 1 is to solve two equations. So part A, we've got an exponential equation 7 to the power of 2x plus 1 is equal to 1,000. And that can be solved in many different ways. The way I would do it is I would rewrite this as a logarithm. So using the rule I've just stated, so 7 to the power of 2x plus 1 is equal to 1,000 is equivalent to log base 7 of 1,000 is equal to the power, which is 2x plus 1. And if you make x the subject, by subtracting 1 and dividing by 2, you get that as an exact answer. You just type that into the calculator and normally round it to about 3SF unless they ask you for something else. So log base 7,000 subtract 1. We'll go for 1.27 to 3SF. Okay, part B is a logarithmic equation. And what you want to tend to do with this is collect the logarithms together and get a single logarithm. Like you want to collect like terms. For this, you want to collect the logarithms together. However, we have to use those three rules above there. The one thing you'll notice about those three rules is for the first two, there's no number in front of the logarithms. But in our one, log, no number in front, but we've got a half in front. So it's really important that the first step you write down is not the subtraction rule or the division rule, but this. The power of a half, or the number of a half becomes a power of a half inside the bracket. And then you can use the division rule, log base 2x over x plus 1 to the power of a half is equal to 1. And using the log rules from before, that is equivalent to base is 2, power is 1, x over x plus 1 to the power of a half. And remember, to the power of a half is another way of writing the square root. So that's the same as 2 is equal to x over root x plus 1. very difficult to solve equations containing square roots unless you square everything to get rid of them, which is what I'm going to do. 4 is equal to x squared over x plus 1. And times by the denominator, you'll get 4x plus 4 equals x squared, to give you x squared, subtract 4x, subtract 4 is equal to 0. And then you solve from there. I'm going to cheat and just do this on my calculator. Equation, quadratic, coefficients of 1, negative 4, negative 4. To give you two answers, x equals 4.83 or x is equal to negative 0.828. If you wrote that as your final answer, you would lose a mark, because even though the quadratic gives two answers, the original equation contains logarithms, and from the sketch above, you can't have a log of a negative number. So if I try to substitute a negative number into that original equation, it will give me a math error. So the only correct answer is 4.83 to 3SF. Okay, let's see what else they could ask you. So we got solve 4 to the x, subtract 2 to the power of x plus 1, subtract 15 is equal to 0. And some of you, without me giving any hints, would struggle with this one. But there is a way to show that, or you can write both of these exponentials to the same base, because currently the base is 4 and the other one is 2. But you can replace the base 4 with something to do with base 2, such as the following. So 4 is the same as 2 squared. So that's the same as 2 squared to the power of x. Which is actually the same as 2 to the x squared. Just swapping the powers around. That's perfectly fine. And 2 to the x plus 1 is the same as 2 times 2 to the x. It's one of the rules of indices. Subtract 15 is equal to 0. And now this is something called a hidden quadratic. Hidden quadratic. If you replace 2 to the x with, say, y, so 2 to the x is equal to y, replace every single 2 to the x with the letter y, you get y squared, subtract 2y, subtract 15 is equal to 0, and everybody can solve a quadratic. Subtract 5, add 3, to give y is equal to 5, or y is equal to negative 3. Problem is, you didn't want to work out what y was. The original equation wants you to work out what x is, so you have to substitute back in 2 to the x is equal to 5, or 2 to the x is equal to negative 3. Some of you will know immediately, without trying to find any solutions, that that has no solutions. 2 to the power of something can never be negative 3. However, 2 to the power of x is equal to 5. To find that, this is the equivalent of log base 2 of 5 is equal to the power, which is x. And I'm going to leave that as an exact number, actually. Log base 2 of 5 is the answer to this, and the only answer to it. So that's a hidden quadratic, which you need to spot. Sometimes they give you a clue that it's a hidden quadratic. This time it didn't. Right. Third and final example is a question with a context. A modelling question, exponential modelling. They tell you the total number of views in millions, V, of a viral video in X days is modeled by this formula. V equals e to the power of 0.4x subtract 1. Find the total number of views after 5 days. Part A, x is 5. If you put 5 into the formula, we've got e to the power of 0.4 times 5, subtract 1, 6.389, so on. And remember, the unit is millions. So I'm going to say 6.4 million to 2SF. Part B. Find dv by dx. So dv by dx. We stated how to differentiate something like e to the power of kx on the previous page. So dv by dx, e to the 0.4x would go to 0.4 e to the 0.4x. You always times by, if the x has got a multiple, you times by that multiple. What does 1 differentiate to? It disappears. So that's your final answer for that one. Part C. Find the rate of increase of the number of views after 100 days. Rate of increase. So that is a really fancy word. Finding dv by dx, because rate means change with time. X is that change in time, changing throughout the days. But find it at a very specific point at 100 days when x is equal to 100. So that written question there in algebraic symbols or calculus symbols, that's what it means, dv by dx when x is equal to 100. So in other words, sub 100 into this. So 0.4 e to the 0.4 100, and then put that into your calculator. 0.4 times e to the 0.4 times 100. Very big number, 9.42 times 10 to the 16. Now it's always important to write your units in these types of questions. Rate of increase. So remember, the units would match up with a fraction for the differentiation. V was views in millions. X was per day. So this is a rate of 9.42 times 10 to the 16 million views per day. That's the rate of increase. Sounds big to me. Part D. Use your answer to Part C to comment on the validity of the model after 100 days. Well, based on that, I was expecting a lot of views. Not exactly sure how many, how to read that number out in total, but it's a lot more than a billion. So this would not be sensible. So this number is too big. Therefore, not valid at 100 days or after. And that would be it. The questions I'd like you to complete are in the review exercise, which is on page, or starts on page 340. And if you start on question 25 and go up to question 30, you could do them in any order you like. And then if you have any questions about those, then rejoin the Teams meeting and let me know.